Section 6.7 is probability and odds. I can find probabilities. Let's say you're rolling a die and want to know how likely you are to roll a certain number. Each time you roll the die, there are 6 possible results. This is an example of an experiment. The results of an experiment are outcomes. When you roll a die, the 6 possible outcomes are 1, 2, 3, 4, 5, or 6. An event is an outcome or a collection of outcomes, such as rolling a 1 or rolling an odd number. Once we specify the event, the outcomes for that event are called favorable events, so things that we want. So if we say we want to roll an odd number and roll a 1, that's good. Okay, the outcome for rolling an odd number, the favorable outcomes for rolling an odd number are rolling a 1, a 3, and a 5. The probability that an event occurs is a measure of the likelihood that the event will occur. The probability of an event, when all the outcomes are equally likely, is the number of favorable outcomes, so the things that we want, or the yeses, over all the possibilities, the number of possible outcomes. So in example 1, suppose we roll a die. What is the probability that we roll an even number? So all the possibilities are 1, 2, 3, 4, 5, and 6. The evens are 2, 4, and 6. So we add them up. The number of favorable outcomes are the evens, which are 1, 2, 3 of them, over the total number, and we said that there were 6 in all. Now, remember, we always want to reduce our ratios. I can take a 3 out of both of them, and I get 1 out of 2. So 1 out of 2 numbers on a die is even. Now, go ahead and pause and try this if you'd like. Suppose we roll a die. What is the probability that we roll a number greater than 1? So again, all of our options are 1, 2, 3, 4, 5, and 6. All of our options, there are 6 total. Of those options, the ones that are greater than 1, 2, 3, 4, 5, and 6. So all of our favorable or our wanted or the yes parts, 1, 2, 3, 4, 5 of them. So 5 out of 6. Experimental probability here. The probability we found in example 1 is an example of theoretical probability. A theoretical probability is based on knowing all of the equally likely outcomes of an experiment. It's based on theory. Theoretically, what would happen if we roll a die 4 times or 6 times is we'd get a 1 once, a 2 once, a 3 once, a 4 once, a 5 once, and a 6 once. But we know that in practice, that doesn't necessarily happen. A probability that is based on repeated trials of an experiment is called experimental probability. And this is what actually happens. Each trial in which the event occurs is a success. So, experimental probability is very similar to a theoretical in its formula. The number of successes is just like the number of favorable outcomes. And the number of trials is just like all of our possibilities. So we want the number of yeses still over all of the times we tried. A miniature golf course offers a free game to golfers who make a hole-in-one on the last hole. Last week, 44 out of the 246 golfers made a hole-in-one on the last hole. Find the experimental probability that a golfer makes a hole-in-one on the last hole. So we're looking for golfers that make a hole-in-one on the last hole. That's our yes. That's our success or our favorable outcome. And here it tells us that 44 made the hole-in-one. That goes in our numerator. In our denominator goes all of the golfers. All of the people who tried, all of our trials. 246. And we can reduce this fraction if we wanted to, but it's still not going to be super helpful. If I have 44 over 246, even at its most simple, all I can do is take out a 2, and I'll have 22 over 123. If I tell you, hey, 22 out of 123 people, that doesn't really help you figure out how likely you are to make one, or you and your group of friends. So another way that we can write probability is as a decimal or as a percent. So if we divide there, our decimal is approximately 0.17886, so 179. We can also write that as a percent as 17.9%. So what is the probability that golfer makes a hole in one on the last hole? 17.9%, which is a little bit easier to think about than 22 over 123. They mean the same thing, but a little bit easier to wrap your mind around. Now go ahead and try this. We interviewed 45 randomly chosen students for the newspaper. Of the students we interviewed, 15 play sports. Find the experimental probability that the next randomly chosen student will play sports. So again, we're looking for plays sports. That's our successes, or our yes, or our favorable. And remember, that goes on top over total number of trials, or total, or all. It said that 15 play sports. That is our favorable. The number of successes and the number of yeses. There are a total of 45 randomly chosen students. That's our total. That goes on the bottom. Now here we can reduce. I can take a 3 or a 5 or a 15 out of each of them, which leaves me as 1 out of 3. And here we can leave that as a fraction if we want, because if I say 1 out of 3 people play sports, that kind of resonates a little bit better in your mind than it did when it was 22 over 123. If you want to, though, you can write that as a decimal as 0.33, or 0.3 repeating, and as a percent as 33.3 or just 33%. So whichever one of those you want to go with, go for it. They all mean the same thing, but here 1 out of 3 is probably the most helpful. If we look in a room and count how many people, a third of them, so 1, no, no, yes, no, no, is a little bit easier to see than it was in the 22 out of 123. Last thing here, interpreting probabilities. Probabilities can range from 0 to 1. The closer the probability of an event is to 1, the more likely the event will occur. Example 3. Today you attempted 50 free throws and made 32 of them. Use experimental probability to predict how many free throws you will make tomorrow if you attempt 75 free throws. So again, we're looking for the made free throws. How many made free throws are you going to have? So yeses is 32, our favorable or our successes, and we attempted 50. So that's our total number of trials. Now we want that same success rate. So we want to know how many free throws. We don't know. Remember, this is our makes, and this is our tries. We don't know how many we're going to make, but we know that we're going to try 75. We can solve proportions a number of ways, but one of those ways is to use cross products. Here we take 32 times 75 equal to our second cross product of 50 times x. When I do that, I get 2400 equals 50 times x. We divide by 50 to get x by itself. Remember, we always move away from our variable, and get 48. So if we had the same probability of success as we did tomorrow, we made 32 today out of 50. Tomorrow we're going to make about 48 out of 75. And again, that's not guaranteed, but based off what we did today, if that pattern continues, we'd have 48 tomorrow. go ahead and try this. Use the information in example 3 to predict how many free throws you would make if you attempted 150 free throws. So again, we want to know how many free throws you would make. Make is the big part. So make is our success over try. We made 32 and tried 50. And now we want that same success. So we don't know how many we're going to make, but we're going to shoot 150. And we're going to see ballpark about how we will shoot. So again, we have proportions. One way to solve them is with cross products. Didn't really work there. Cross products. 32 times 150 equals 50 times x. When we multiply 32 and 150, we get 4,800. And then to get rid of the multiplication, we have to divide. So we divide by 50 and get 96. So based off the 32 out of 50, if we shoot 150 or 3 times as many, we're going to make 96, which is 3 times as many as today. Last thing for section 6.7 here is odds. When all outcomes are equally likely, the ratio of the number of favorable outcomes to the number of unfavorable outcomes is called the odds in favor of an event. So favorable outcomes is odds in favor when we compare that to unfavorable. So favorable to unfavorable, just like our formula right here, is odds in favor. The ratio of the number of unfavorable events to the number of favorable events is called the odds against. Okay, so odds against compares unfavorable to favorable. Same idea here, just backwards. So whether we want yeses to nos or nos to yeses. The difference with odds versus probability is that we're not comparing to the total here. We're comparing yeses to nos instead of yeses to alls. So, suppose you randomly chose a number between 1 and 20. What are the odds in favor of choosing a prime number? So, I put the numbers 1 through 20 here. We want odds in favor of choosing a prime number, which means we need the prime numbers. 2, 3, 5, 7, 11, 13, 17, and 19. Odds in favor of choosing a prime number means these are our yeses. These are what we want. And there are 8 of them. And we compare that to the odds against the things that we don't want. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, all the things that are not prime. Okay, if we want odds in favor of choosing a prime number, everything that's not a prime number is against it. We can reduce this by 4 and have 2 over 3. So our odds are 2 to 3 choosing a prime number. The odds against choosing a prime number, well, we said that there were 12 that were not prime number and 8 that are prime numbers. So here, again, we can reduce by 4 and get 3 to 2. Here it's not prime to yes prime. Here it's yes prime to no prime. And that's the difference between odds in favor and odds against. And that's all for section 6.7.